Okay, let's just jump right into this explainer. Back in 1887, Albert A. Michelson and Edward W. Morley essentially set out to map the universe. But instead, well, they executed what is probably the most successful failure in all of scientific history. We're going to unpack this incredible moment in time when the absolute greatest minds in physics built an incredibly precise machine hoping to measure something fundamental about the cosmos, only to find, literally, nothing. But as you'll see, that nothing ended up changing absolutely everything.
Seriously, I want you to keep this question in mind as we go. What if the greatest experiment in physics actually failed to find what it was looking for? In science, we're so often taught that a null result, just a straight-up failure to prove a hypothesis, is a total dead end. But today, we're going to see exactly how this particular dead end gave birth to modern physics.
All right, Section 1, Luminiferous Aether Wind, Hunting the Invisible.
Let's look at the actual ghosts these scientists were trying to hunt down. Because every other known wave, like sound traveling through air or ocean ripples moving through water, needed a physical medium, 19th century physicists naturally assumed light required one too. And honestly, it made perfect sense at the time. If the light from distant stars is reaching us, it must be rippling through some invisible, universe-spanning substance. They called this presumed medium the luminiferous ether. To really visualize this, imagine a flowing river. Just like Hippolyte Fizeau demonstrated with his 1849 water experiment, a wave moving with the current travels noticeably faster than a wave fighting against it. So the thinking went, as the Earth hurtles through space, it should be plowing through this stationary ether, kicking up an ether wind. Light traveling against this wind was predicted to travel just a tiny fraction slower than light traveling perpendicular to it.
Michelson and Morley realized they could actually use these minute speed differences to pull off something incredible, determining the Earth's absolute motion relative to the ether. If they could measure the change in the speed of light based on which way their equipment was facing, they could essentially map our exact speed and direction against the absolute backdrop of space. Pretty ambitious, right?
Moving right along to Section 2, Splitting the Light with the Interferometer.
To measure something so infinitesimally small, they had to build an incredibly precise instrument. Basically, a beam of white light hits a semi-silvered mirror, which acts as a beam splitter. Half the light shoots straight through, and the other half is reflected at a 90-degree angle. They travel to mirrors at the end of their respective paths, bounce back, and recombine at an eyepiece. And because they come from the exact same source, the recombined light waves interfere with one another.
Now, to test this ether wind from all different directions, they actually floated this massive equipment on a bath of mercury. Why? So it could rotate seamlessly with minimal friction. The optical path was a massive 11 meters long, which they achieved by bouncing the light back and forth. Floating this heavy optical bench on mercury meant Michelson and Morley could slowly, smoothly turn the entire apparatus without introducing even the slightest vibrations that might ruin their sensitive optical alignment.
So what were they looking for? Well, the resulting interference pattern looks like a bullseye made up of concentric circular fringes. The theory was, if the Earth was indeed moving through the aether, rotating this device would shift those fringes. If the speed of light changed even a tiny bit in one arm compared to the other because of that aether wind, the crests and troughs of the light waves would arrive just slightly out of phase, visually shifting those circles across the eyepiece.
Which brings us to Section 3, the famous null result, finding nothing.
This was the big moment of truth. Michelson, who, by the way, would later win the 1907 Nobel Prize, and Morley were completely ready to observe the universe's absolute frame of reference. Because the Earth orbits the Sun at roughly 30 kilometers per second, they expected a phase shift of 0.4 fringes. They took their measurements, rotated that heavy mercury table, took more measurements, and waited for the shift. Now keep in mind, their equipment was sensitive enough to detect a shift of just 0.01 fringes, but the instrument detected virtually nothing.
An absolute zero, the famous null result. And this absolutely perplexed the scientific community because it completely contradicted Galilean and Newtonian physics. Under the established rules at the time, velocities were supposed to just add up. If you shine a flashlight forward from a moving planet, that beam should be moving at the speed of light plus the speed of the planet. But the Michelson-Morley experiment loudly declared, nope, it doesn't.
That magnificent failure basically forced three universe-altering conclusions upon us. 1. The ether does not exist. 2. There is no absolute motion. Everything is relative. And 3. The speed of light is invariant, meaning it is exactly the same for all observers no matter how fast they're moving or in what direction. The universe isn't some fixed stage with an invisible medium. This was a profound shock to classical physics.
All right, moving into Section 4, the Einstein mystery, memory versus history.
So this null result directly paved the way for Einstein's special relativity. But history actually presents us with a really fascinating whodunit here. Later in his life, acting as a believing rationalist who valued mathematical elegance over empirical experiments, Einstein claimed the Michelson-Morley experiment played no decisive role in his thinking. In the 1940s and 50s, he routinely told historians he was already convinced absolute motion didn't exist for purely theoretical reasons. He basically brushed off the experiment as just a nice little empirical confirmation of what his beautiful math was already telling him.
But wait, it gets better. A newly uncovered transcript from a 1921 lecture in Chicago reveals a stark contrast. A younger, much more empiricist Einstein flat out admitted that learning of Michelson's null result as a student showed him that thinking of the Earth moving against the aether was our big mistake. It's just a wonderful reminder that even the absolute greatest scientific minds tend to, well, reshape their own histories over time.
Finally, Section 5, modern interferometers and the technology we use today. Despite being designed to hunt for an ether that flat out didn't exist, this 120-year-old design remains an incredibly vital piece of technology today. Advanced physics labs still use interferometers, often swapped out with Hine lasers and CCD sensors, to do everything from teaching undergrad students to detecting minute vibrations to literally measuring the precise refractive index of glass. Oh, and when the LIGO Observatory detected the unimaginably faint ripple of two black holes colliding a billion light-years away, yeah, they used an interferometer. The sensitivity of Michelson's basic optical setup is still just absolutely unparalleled.
Michelson and Morley accidentally unmoored us from absolute space, effectively handing Einstein the keys to relativity. It really makes you wonder, if the most famous null result in history revolutionized physics, what future discoveries are hiding in today's failed experiments? Think about that the next time you hit a dead end. Thanks for joining me on this explainer, and as always, stay curious.